Welcome back. We're going to talk about sigma and pi bonds. The emphasis is on that last part with bonds. When we talk about shapes and angles, we have to refer to the bonds for the shape, but the lone non-bonding pairs affects the angle. When we talk about hybridization, you have to refer to all the pairs of electrons, positions in space. Well, this is a sigma and a pi bond, so only referring to the actual bonds themselves. When we're talking about single atoms without any kind of bonds, we would have the spherical ones would be called an S, and then the double lobe would be called the P's. And they would exist in the middle. This would be the middle of the atom. This would be the middle of the atom, and they would have all these within it. Each orbital would contain a pair of electrons and only a pair of electrons. Well, we're going to morph these into different shapes. So the S and the P refer to the sigma and pi, but they're not exactly the same. And once again, they're only for bonds. So if you had something like a carbon single bond carbon. Now, obviously, we wouldn't have just carbon. There'd be more bonds coming off here to do other things. We're just not going to focus on that. We're going to talk about the carbon, single bond carbon. And if that's the carbon atom, and then that's the other carbon atom, we would have a hybrid bond in which you would have this guy, and it would overlap, and then this guy, and overlap, and then you would have this thing come across the middle. So this big area across the middle would be a bond. This is an area in which the electrons would move. And the first bond you get when you have a single bond, the area in the middle is going to be taken up by this pair of electrons. And so this one would be called a sigma bond. It's a lowercase sigma. So you can type an S, a lowercase s in Word, and then change the font to symbol. And it turns into a Greek letter, and it'll turn into a sigma. Speaking of, this looks like Sid the Sloth. Sid the Sloth from Ice Age. Well, maybe not. All right, so that space is taken up, and then that's it. So if you have another bond thrown in the mix, so we're going to have, and I guess I should color coordinate this so that these are going to be the red guys. And then the double bond, well, it starts off the same way. Again, there's more things coming off this carbon, but not between the two carbons. So if you look at these carbons, you're going to have this guy right here, this guy right here, and the first area that's taken up is right across the middle. Because it's a low energy position. For electrons to travel, they travel right across the middle here, and that would be one sigma bond. Just like up here is one sigma bond. Now, for the other pair of electrons that's involved right here, they can't go in the middle. They can't have more electrons than two traveling inside an orbital, and so they have to go someplace else. So they're going to go up and around. And the way you kind of draw this is draw almost like a p orbital, like this, and then you overlap it on the top and the bottom. And so this is where this whole area is where a second pair of electrons would travel. If you look down here with your little eyeball, like this, you would see the s orbital, which is a big ball, and then you would see the other orbital, which is the pi bond. Ooh, that's pretty sad. Try it again. May not be any better. So you have the pi bond. So this is going to be one sigma and one pi. So every time you have a covalent bond, you have a sigma bond. And every time you have an additional stick in there, you have a pi bond. Okay, well, let's say that you had a carbon with a triple bond. Let's go with this color. Well, you're going to have the original bond over here. and it's going to overlap. Oh, that's just horrible. It's going to overlap top and bottom, and all that space is taken up. And then you're going to have the vertical, because the pi bonds are planar, you're going to have the vertical pi bond like this, overlapping top and bottom. They're going to be flat and planar, and therefore they cannot rotate. When we get to organic chemistry, we'll see when you have a single and a double, there is no rotation across this, and it sticks it in place. So here we have the sigma bond. Here we have the vertical pi bond. And then we have another set of electrons. So that's to go somewhere. So they're going to be an identical pi bond that's going to be 90 degrees off of it. And again, if you look down like this, it's going to look like this guy. So we're going to have one sigma, and we're going to have two pi. Over here in this drawing, it's going to look a little weird. This is where we're going to really screw it up. So you're going to have them coming out of the plane of the board and going back into the board, out of the plane of the board and going back into the board, and then they overlap like this. So this is much more messy now. They're 90 degrees off each other, and so over here, it might be a little easier to understand what we're looking at. There would also be no rotation on here, but if you had this guy coming off, it'd be a linear thing, so it wouldn't matter if it's a rotation or not. All right, so that's what you have. Every time you have a bond, you have a sigma bond. Every additional stick is going to be a pi bond. So a lot of times they'll ask you to define it. To define it is the shape. A sigma bond is a head-to-head axial overlap, as in an axis, as in like on a car where your wheels are attached and they go straight across. That is like an axis that rotates around. And then a pi bond is going to be a side-by-side overlap in which the electrons go over the top and bottom. Okay, side-by-side overlap in which the electrons go over the top and bottom. Here we have a compound called ethanal. Eth means two carbons, and means the carbons are going to be single bonded to each other, and al means an aldehyde, which is a double bonded oxygen on the first carbon. We will learn all this in organic. Now, how many sigma and how many pi's are there? So you have sigma and you have pi's, and you got number and number. All you gotta do is count the bonds. 1, 2, 3, 4, 5, and 6. That would be 6 sigma bonds. And oh, by the way, this additional stick right here is going to be a pi bond, so 1 pi bond. The lone pairs do not play a part in it. They would if we're talking about hybridization, but not with sigma pi bonds because we're referring to the bonds. Fairly large molecule, and it says how many sigma and how many pi. Well, okay, so let's see, here we go. Sigma bonds, pi bonds. By the way, the Greek letter for pi, this is an uppercase pi and this is a lowercase pi, just like our p's. So technically it's a lowercase pi, but it's kind of hard to tell. Okay, so let's count the bonds. You got 1, you got 2, you got 3, 4, 5, 6, 7, 8, and don't forget the OH. This is what organic does. They stick it together, but OH is not an element. There's actually a guy right there that's a bond. Technically, this guy is going to be bent like water, 104.5 or less than 109.5 and 2 lone pairs. But it's not always shown that way. So, how many we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 total covalent bonds and therefore 9 sigma bonds. Now, each additional stick, 1 right there, 1 right there, and 1 right there. That's 3 additional sticks, so it's going to be 3 pi bonds. Organic will do skeleton structures, which you are not going to do, and you really aren't really have to know it too much. They're pretty easy once you get to it, but we haven't gotten to organic yet. Basically, every end of a line is a carbon. Every angle is a carbon. And of course, any single line is a single bond, double line is a double bond. Organic is all about hydrocarbons. So the hydrogens stick on there. So if we wrote this thing out, we would have 1, 2, 3, 4, 5, 6 carbons and a double bond between the second and third. So carbon, carbon, double bond, carbon, carbon, carbon. 1, 2, 3, 4, 5, and 6. So we will sprinkle in the hydrogens to make it work. We know that carbon needs 4 sticks all day. Not 4 bonds, but 4 sticks. That first one needs 3 more, so we put 3 hydrogens. This one has 3 sticks, it needs 1 more to make it 4. This one has 3 sticks, 1 more to make it 4. Up or down doesn't really matter unless you know the structure, unless you know some more geometric structures. This guy has 2 sticks, so it needs 2 hydrogens, 1 up, 1 down, just for space. Same thing here. And this last one only has 1 stick, so it needs 3 more. Okay, how many sigma pi? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Woo! We're going to have 17 sigma bonds and 1 pi. I brought up the skeleton structures because even though we're not there yet, we will be talking about this particular structure called benzene. Benzene is going to be the main chain. If it's actually on a branch, we're going to call it phenyl. But this is benzene, and they often, almost always, draw it as a skeleton structure. This thing has a resonance structure, which if you haven't gotten to, we will. And this is how it's drawn. So it looks kind of small, like not a big deal. However, this is what it really is. So all the hydrogens are deleted, and it essentially has an alternating single double bonds. So if it was benzene by itself, how many sigma and how many pi? Well, let's put a sigma, let's put a pi, put equals and equals. Sigma, well, there's 6 hydrogens, so it's 1, 2, 3, 4, 5, 6. And there's 6 carbons in a ring, so 1, 2, 3, 4, 5, 6. So that's 6 and 6, so that's 12. 12 sigma bonds. The pi bonds, there's 1 there, there's 1 there, and there's 1 there. Even when we discuss the delocalized system, we would still refer this to having 3 pi bonds. I hope this helps.